So we've already seen that a hub, every single port is the same collision domain and it's all in the same broadcast domain. And we've seen that in a switch, in its default configuration, every single port is its own individual collision domain, but the broadcast domain encompasses all the ports. So now the next thing to look at is VLANs. So what I've done, I've set 3 different VLANs, VLan 10, VLan 20 and VLan 30 on this switch. And I put PC1 and PC2 into VLan 10, PC3 and 4 into VLan 20 and PC5 and 6 into VLan 30. So the idea of using VLANs is that you can logically separate the ports, so only ports that are in the same VLAN can communicate to each other. So effectively what we've done is we've made these ports here their own collision and broadcast, these ports there their own, and these ports here their own. So PC1 cannot communicate with PC3, so any broadcasts that are sent out for the likes of any ARPs or anything like that will only go within the actual VLAN itself. So any ARP request will only go in VLan 10, so it'll only hit PC2. The same with VLan 20, any ARPs that are sent from PC3 will only be sent out the port to PC4, and exactly the same for VLan 30. Any ARP requests, any broadcasts that go from PC5 will only reach PC6. So if you can imagine that if this is a business and these PCs are, for argument's sake, web servers for different applications, you've effectively split off all of these different departments so they're only located within their own address space. Let's have a look and see what we can find. So firstly, let's have a look at PC1 and let's see if we can ping to PC3. Let's have a look. So we do ping 10.10.10.3 and let's see what happens with that. Okay. So as you can see, an ARP goes out. Oh, and did you notice there that the only port that you could send the ARP request out from was to PC2, because they are the only 2 devices which are in the same VLAN. So what's happening now is this PC1 is unable to find the address of PC3 because it's not on the same VLAN, so they're completely separated. And as you can see, PC2 is dropping the packets. PC1 is going to continually send out these ARPs for a while to say who has the IP address of 10.10.10.3, and the only thing the switch can do is send it out another port that is within the same VLAN that PC1 is on. Eventually it will drop and it will stop sending these ARP requests. But as we can see, we've successfully managed to separate the broadcast domains. So broadcasts on between PC1 and PC2 are not going to interfere with anything else. So if this was a big, busy production network, then you've really limited the amount of traffic that's being unnecessarily generated. As we can see from the ping results, it timed out. It just could not find it. So if we have a look at the actual switch, have a look at the MAC address table and see what's on there. We only have an entry for PC1 on Fast Ethernet 01. Because PC2 never replied, it doesn't know the MAC address of PC2, and of course PC3 didn't reply either. So let's send a ping to PC2 and let's have a look. So it's going to send an ARP request out again to say who has 10.10.10.2. The switch is going to flood it out of every single port that is in the same VLAN. However, PC2 should now reply to say, I have this IP address. As we see, there's a reply now going back. So it's hit the switch, it's now going to go back to PC1, and PC1 now knows its MAC address, so it can actually fill out its IP packet with the destination MAC address and send it to the switch. But now, because the switch has already received a packet from PC2, it knows what port PC2 is located on. So now we've got unicast packets being sent back between PC1 and PC2. Okay, so as you can see, we're now getting replies in the terminal there. So if we have a look at the MAC address table now, we now have two entries, one for PC1 and one for PC2. And just to prove that that's actually working as intended, let's pick on, say, PC6 and PC5, because they are both in VLan 30. We'll just give it a moment for these pings to complete. Now, what we do know is that the switch knows where PC1 and PC2 are located. So we will try and ping PC1 from PC6 and see whether or not that will actually work. Okay, so we're going to create this packet now, and we'll see if we can get the ping to go across. So just waiting. Hopefully that's the last reply for that one. Okay, that's looking sweet. Alright, so PC6, as you can see, is going to now do an ARP, say where is the address of PC1. The switch knows where PC1 is connected to. However, it's not on the same VLAN, so it's going to broadcast it out again. So it's broadcasted it out to PC5, which is on VLan 30. And of course, PC5 doesn't have that IP address, so it's like, that's not for me. So the packet's just not going to be sent. So there's no communication now between PC6 on VLan 30 and PC1 on VLan 10. So these three VLANs and any devices and ports that are in these VLANs are completely separated from each other. So we now have three different broadcast domains. We have a broadcast domain for VLan 10, a broadcast domain for VLan 20, and a broadcast domain for VLan 30. And what we'll do, as soon as these request times out, which should only take a moment. Now, normally this goes extremely quickly. If I take it out of simulation mode and go to real time, that will speed it right up. All right, let's go back in now. So let's now try to ping PC5. Before we do that, let's double check, because there was some packets going back through to PC5. It flooded it out. Let's see if the switch actually learnt it. No, it didn't. Okay, so all it's got on VLan 30 is the packet it received from PC6. Because it didn't receive anything for PC5, it has no knowledge of it. Let's carry on with this ping then, and we'll see what happens. So PC6 again is going to send an ARP request to the switch, and the switch is going to flood it out of all the ports that are in the same VLAN that it's connected to, which in this case is VLan 30. So it's going to send it to PC5, but this time PC5 is now going to reply and say, this is now for me. So it's replied back to the switch. So the switch has now received a packet from PC5 and now it's put its MAC address into its MAC address table. PC6 now knows the MAC address of PC5, so now it can start sending packets directly to PC5. As we can see there, that's been successful. If we look on the switch now, we should see PC5's MAC address is also there. So we've got a MAC address entry for PC5 and PC6. And as you notice, one's on VLan 10, one's on VLan 30. Again, as I've said before, I know this is Cisco's packet tracer, but this is so just so it can be visualized, really. I mean, this works exactly the same way, whether it's on a Cisco switch, whether it's on a Juniper switch, whether it's on an Aruba switch, or a Black Diamond switch. It doesn't matter. Switching works the same regardless. Well, I hope this has been interesting for you, and thanks for watching. Hello and welcome to the IPv6 address section for the Juniper JNC IA. So the agenda for this video is we're going to have a look at what is an IPv6 address, why are they used, the types of IPv6 addresses, and the changes between IPv4 and IPv6. So as an introduction, an IPv6 address, it's a unique address that identifies a device on the internet or on your local network. And IPv6 stands for Internet Protocol version 6. Now, as you know, we have IPv version 4. There was in the late 90s an IPv version 5, but it was never actually released. It was just like a candidate version, so they skipped it and went straight to IPv6. So IPv6 addresses are the direct update to IPv4, and they're used to combat the global IPv4 address shortage. Many network services have also been rolled into the IPv6 protocol. So you have the likes of ICMP, you have ARP, and you have a few other protocols that are automatically rolled into IPv6 now. So an IPv6 address is a 128-bit string of hexadecimal numbers separated by colons. Compare that to an IPv4 address, which is only 32 bits long. So for example, 192.168.1.1, that's only a 32-bit address. IPv6 addresses are expressed as a set of 8 groups of 4 hexadecimal numbers. So as we can see here, we have 4, 4, 4, etc. all the way to the end, which this will be 8 lots of them. So each number in the range can be 0 to 9 or A to F because it's hexadecimal. The full IP address range gives a total usable space of around 3.4 times 10 to the power of 38. So that's like 340 undecillion unique addresses. Compare that to the meager, just under 4.5 billion addresses that we have currently for IPv4. So IPv6 has been around for around 25 years. However, it's only in the last 10 years or so that networks have been adopting it. So India by far has the highest adoption rate of around 60%, and that in the US it's around 40%, and in Europe the range is anywhere between 38 to 53% depending on the country. So the Internet Assigned Numbers Authority maintains the global IPv6 addresses, and it allocates these to the regional internet registries, the same people that basically allocate out the IPv4 addresses. So we have some multiple different address types here. So we have first our global unicast addresses. These are routable on the internet and start with the 2001 as their prefix. Now global unicast addresses, these are equivalent to IPv4 addresses. So if we go back and see this address that we have here, 2001 0db8, etc., that will be that would actually be classed as a routable address. So that will be known as a global unicast address. So then we have our anycast addresses. These are, sorry, our unicast addresses. These are used to identify an individual interface on an individual node. So if you have two nodes together, so you have router, and you have a connection between them, these links here would be unicast. Okay, so then you have your anycast addresses. These are used to identify a group of addresses on different nodes. So basically, let's say you have your internet here and you're here in your house, and let's say here is the US and here is Europe, and you want to get to Google, for argument's sake, 8.8.8.8, well, you don't have to, and let's say we know Google's generally hosted in the US, you don't have to travel all the way to the US first, because that 8.8.8 can be an anycast address. So you can have multiple different instances of anycast addresses in IPv6. So that means that you can be routed to the nearest instance of that address rather than having to go all the way to where it actually resides in, let's say, America, for argument's sake. So then you have your multicast addresses. These start FF00::8, as we can see there. And these addresses, these are basically used to define multicasts. And these are used to send basically single packets or single flows of data to multiple destinations at a time. You may already know things like routing protocols, things like that, which will use multicast. But you'll also have things like, let's say, Netflix, for argument's sake. You're sitting at home and you're watching Netflix on your TV, and you're watching, let's say, the latest series of Stranger Things. Well, one of your friends might be in their home watching the same episode, and there could be like thousands of other people across, say, the UK watching the exact same episode as you. Well, they're all part at that time of a multicast group, so it means Netflix just needs to send one set of streams generally to service everyone, rather than just having to send a complete fresh stream to everyone at the same time. That's what makes multicast quite good. So then you have your link local addresses. These start at FE80::10. So this is one of the two internal address types, but they're not routed on the internet. Link local addresses are used only inside an internal network. Then you have your unique link local addresses, which start FD008. This is the other type of the internal addresses. Again, they're not routed on the internet. These are again within the LAN only, but these are the equivalent of the what's called the RFC 1918, or the private IP address space. And then you've got your loopback addresses. Now, these are the direct replacements for the 127.0.0.0 range, and they're expressed as ::1/128, or all of these zeros and then a 128. It's up to you how you do it. You can put it in either way. It's entirely up to you. Let's have a look at the address format. So in IPv6, the address is split into two sections: the network section, which we see here, and the node section, which we can see here. The address splits basically into two 64-bit segments. The upper top, or the upper bits, is the network section, and the lower bits is the node section. So the upper bits are used for internet routing. So these will be your, let me move that there. So these there will be your what will be allocated by your ISP, and the node section will be what you'd have for your end devices. Okay, sweet. Okay, so the lower 64 bits identify the addresses of the interfaces or the nodes, and it's derived from the actual physical or MAC address using the extended unique identifier or the EUI-64 format. The upper 64 bits is basically again split into two blocks, one of 48 bits and one of 16 bits. The lower 16 bits is used for subnetting. So these bits here are used for subnetting, and if you haven't gone across subnetting, we'll go over that in some more videos afterwards. The upper 48 bits are used for the global network address, and they basically used for routing over the internet. So the benefits of IPv6 is we get more efficient routing. So IPv6 reduces the size of the device's routing tables and basically makes routing more efficient. IPv6 networks with fragmentation basically is handled by the sending device rather than the every router in the path. So it's using the protocol called MTU discovery to discover the MTU, the maximum transmission unit, or the largest size of packet that can actually be sent over the network. This basically means that there's virtually no fragmentation that goes on. So there's more efficient packet processing. So compared to IPv4, IPv6 contains no IP level checksum. So the checksum doesn't have to be recalculated basically at every single hop. So direct data flows. So IPv6 supports multicast rather than broadcast. So multicast allows bandwidth intensive packets to be sent from multiple destinations simultaneously, basically saving network bandwidth. And I said multicast, I said broadcast there, but I actually meant multicast. I do apologize. So simplified network configuration as well. So IPv6 devices can be independently auto-configure themselves when they're connected to other IPv6 devices. So for argument's sake, you can bring your router online now, and it can be connected to another router, and it can pull its IP address down from, let's say, this is router 1. So we can pull its IP address down. It can pull down its what subnets it's on. It can pull down, if you have the other one configured automatically, it can pull down things like its domain names. So again, these are what some of the advantages of IPv6, because these are built into the protocol itself. So let's have a look. So security, so IPv6 security is already enabled. I mean, it supports IPsec out of the box. So if you want to configure IPsec on IPv4, it's a little bit of configuration, but with IPv6 it's already built in. Data is generally quite secure. So this is how the header of an IPv6 looks like. So we have our version, which of course will be version 6. We have our traffic class, which is our TOS, which we can mark a particular packet to say what sort of priority we want on the network. We have our payload length, we have our flow labels, and we have what's called the next header, which basically informs the receiving device what the next packet's going to be. We have our hop limit, which is our TTL, our source address, and our destination address. The header is actually relatively simple for IPv6. We're going to have a look now on the next slide where we can compare the two of them. So as you can see here, the IPv6 header on the right is, while it's wider, as you see, that's just the picture image itself, but you can see how many few fields it's got to worry about. I mean, compared to IPv4, there's a lot of things that have actually been taken out. So they both share, version control, version. They both have source and destination addresses. As you can see, we have payload here. That will be data. Okay, you have your traffic class, and you got your type of service there. Next header is new. Name has been changed. The next header would be will be header checksum actually on that one. The hop limit is our TTL, which is here somewhere. There we go, right there. Sweet. So as we can see, the headers themselves is an awful lot more simple compared to the IPv4. So let's have a look at our quick Wireshark capture of IPv6 so we can see what's going on with this. As we can see, we have our layer 2, but here's our layer 3 information, and it's telling us that we are running version 6, and you can see the IP address, so the source address here, which is FE80. We see there, we can see our destination addresses. So these are our private addresses, these ones, and as we can see, our source and destination MAC addresses are also included. So nothing changes at layer 2, it's only at layer 3 that things change for IPv6. Well, there you go. I hope you found this interesting quick introduction to IPv6, and I look forward to seeing you in the next video. Hello and welcome to the IPv4 address section of the Network Fundamentals for the Juniper JNCIA. Okay, so the agenda for this video is going to be what is an IPv4 address, where are they used, the types of addresses, and the IPv4 future. So an IP address is a unique address that identifies a device on the internet or a local network. IP stands for Internet Protocol, which is the set of rules governing the format of data sent via the internet or on the local network itself. IP addresses are the identifier that allows information to be sent between devices on any network. They contain location information and make devices accessible for communications. The internet needs a way to differentiate between different computers, routers, and websites. IP addresses provide a way of doing so and form an essential part of how the internet works. So what is an IPv4 address? An IP address is a 32-bit string of numbers separated by periods or full stops. An IP address is expressed as a set of 4 numbers, each being an octet. An example address might be 127.168.1.55. Each number in the set can range from 0 to 255. The full IP address range goes from 000, so anything in that range, all the way up to 255, 255, 255, 25, which gives us just short of 4.3 billion addresses. IPv4 is a connectionless protocol and operates on a best efforts delivery model. It does not guarantee delivery, nor does it assure proper sequencing or avoid any duplication delivery. Upper layers of the TCP/IP model that you've seen in the previous video take care of that. That would be TCP. The Internet Assigned Numbers Authority maintains the global IP addresses and allocates these to the regional internet registries. They then allocate this out into their regions, i.e. the UK or Europe, and the regional internet registry for Europe is RIPE. So, public address space. A public IP address is an IP address that can be accessed directly over the internet and is assigned by the local registry to your internet service provider. Using a public IP address to connect to the internet is akin to a postcode for data. All public IP addresses are known and are in the ISP's global routing tables. For those of you who don't know what a postcode is, if you're across the pond, that would be the same as your zip code, for argument's sake. At present, there are about 3.7 billion total public routable IP addresses. While the previous slide advised a total of just under 4.3 billion addresses, nearly 600 million addresses are reserved or are not routable. All public IP addresses fall into one of the following predefined public address ranges below. We won't go through all of these because there is quite a lot. But if you take a little screenshot, you'll be able to make a note of those. So the private address space. Now these are covered by RFC 1918. If you don't know what RFC is, an RFC is a request for comments. It's a technical publication that is used as a standard for particular protocols. If you just do a Google for RFCs, you can do a little bit of light reading before bed. So for devices and networks that are not directly connected to the internet, private IP addresses. These addresses are not routable outside of the network that they reside on. NAT is used for that, and we'll have a brief overview of that shortly. It doesn't matter if the same IP is also assigned on a different private network. Because private IP addresses need to be unique only within the local network. So for example, your PC at home might have the IP address 192.168.110, and my laptop may have exactly the same private IP address. However, because our networks are different, it basically doesn't matter. The private address ranges are as follows: 10.0.0.0 to 10.255.255.255, 172.16.0.0 to 172.31.255 to 172.31.255.255, and probably the most common one you're probably familiar with is within this range here, which is the 192.168.0.0 to the 192.168.255.255. Now, your home router will most likely be giving you something in the range of 192.168.1 something on average. Each device on the same network must have a unique address, and with this, so many private IP addresses are available. A business, so for argument's sake, can accommodate all their devices on the local network. They can have hundreds and hundreds of devices, and they can all be using private IPs. Because the limited number of IPv4 addresses led to the practice of sharing one external IP, we're all eventually switching from IPv4 to IPv6 over the next few years, and soon we won't be using IPv4 addresses at all. Your internet service provider gives you one public IP address, and this is on the outside interface or the outside connection, i.e. your router leading to them or your company's main exit router. Your inside network or your LAN has all your private IP addresses. However, when they need to connect to the internet, the public address is used. This has helped to conserve the IPv4 address range. See, you could have, for argument's sake, 10 or more devices at home, but you'll only be using one public IP. Businesses have seen the growth of devices, and they'll be sharing a handful of IPs at most for public routing. Okay, so here's just a little IPv4 example. So this here, imagine this router here, this is your home network. This interface here will be given a public IP address from your internet service provider. We're going to say it's BT or British Telecom in this case. And this router will take that public IP address and keep it only on that interface. Everything behind, all of these devices, your PC, your laptop, these will all be given private IP addresses. and that's absolutely fine. The PC and the laptop can communicate with each other absolutely fine on their private IPs, but anytime they need to communicate, let's say with this web server over here, they'll send their information over here. They'll send their information out, and then it will be sent with the public IP address to your service provider, in this case BT, and then BT will then send it to maybe another service provider where they would use something that's called carrier grade NAT IP, which is still kind of public within the network. Okay, so what happens now though is that you've got your smartphone here. So your smartphone is connected to your local cell tower. This will be a public IP address. And of course, the cell tower will connect into another service provider, also using a public IP. However, when you decide you get home and you want to use your smartphone, and you turn on your home and use your smartphone and you turn on your home Wi-Fi, that public IP is no longer used. It's now using your private IP internally, and then it's going to be routed off via the internet this way. So the take from this is anything that is inside your network is private, and basically everything outside of your home router or your business's router is a public IP address. Okay, so we're going to have a quick little look at the IPv4 header. Every single packet that uses IPv4 follows the same header format. A version, you need to remember this is 32-bit all the way across that way. And you've got your header length. And you've got your service type. Now the service type, it would be things like your quality of service, stuff like that. And then you have your total length field. You have an identification field and your flags. You have your fragmentation offset. Now this is to make sure that a packet has not been fragmented, where it's been chopped a little bit and only a little bit of the packet's been sent, and then the fragmented part will be sent again afterwards. That's what the fragmentation set does. You've got your time to live, or your TTL value, and you also have your protocol. And then you have a header checksum, which just ensures that everything within the header is working fine. And then you have your destination address. Now, if you were sending information from one device within your local network to another device within your local network, both the source address and the destination address will be private. However, if you're sending via the internet, you're sending it publicly, then both your source and your destination addresses will be public. And then the last part of the header is obviously your data that you're sending. So what we're going to see here is, this is a TCP packet, so this is a web request that's been sent off. So as we can see here, this is the IPv4 header, and as we've seen, we have our version, we have our headers, we have our total length, we have our total length, we have our flags, our fragments offset, our TTL, our protocol, which is TCP in this case, because this is a HTTP request, and you have your header checksums, and you have your source address, and you have your destination address. So this is what it looks like when you're using a TCP packet. Now you need to remember that TCP is layer 4, whereas IP is layer 3. So anything after the IP is irrelevant. It's going to look the same. The next slide has a UDP packet which has been sent out. So as you can see, the UDP packet, again, is exactly the same. For the IP part of it, you have your version, you have your header length, your disk field, or your type field, not your type field rather, the services field. Now this is again for your QoS and things like that. You have your total length, you have your flags, your fragment offsets, your TTL, the protocol, your source, and your destination IP addresses. So at layer 3, the IP packet is the same. It doesn't matter what comes after that, whether it's UDP, whether it's a TCP data. It makes no difference whatsoever. The packet itself is always the same for the header. So the IPv4 future. So IPv4 addresses are now depleted, which means the internet registries are no longer have blocks of IP addresses to give out to service providers. This was a major problem because in the old days when IPv4 first came out, you had lots of businesses and institutions that bought blocks of millions of addresses. They were just given out like sweeties in the shop. They were given millions and millions of addresses, and it ended up that some of them were only using a tenth, if that, of the addresses, and even to this day they're still only using them, but the addresses can't be reused for anyone else. So the registries, they were giving IP addresses out like crazy, and now we're paying the price of that because there are basically no more IPv4 addresses to give out. Service providers now have to reuse the limited blocks that they currently have. So while use has helped conserve the limited amount of addresses that was remaining, other methods have had to be found as well. So we have things that's called carrier grade NAT. Now this is used in service providers with the IP address range of 100.64.0.0 to 100.127.255.255. Now this allows public routing within the service provider's network only. However, some service providers have massive MPLS networks that can span an entire country. So having this sort of address range frees up an awful lot of normal public IP addresses. So IPv6 is the new standard of IP, which does away with the public and private address concepts. It's estimated to be able to provide routable IPs for every device that everyone in the world could ever use for the next couple of 100 years. I did read one report that it's believed that there will be more addresses on IPv6 than there is grains of sand on the planet. Whether that's exactly true, because no one's obviously counting all the grains of sand, but it's a lot. So as we know, IPv4 has a total of about 4.3 billion addresses, which is 4.3 times 10 to the 9, so that's 9 zeros. IPv6 has a mouthful of addresses. I can't even pronounce it. I'm not even going to write it down. It's just absolutely crazy. But it has 3.4 times 10 to the 38. That's 3.4 with 38 zeros at the end. That is a crazy amount. So IPv6, I mean, it's been out for about 20 years or so, IPv6, but the uptake is extremely slow. A lot of people and a lot of businesses, if they can get away with it, don't actually want to be using IPv6 at the moment because it's big overhead for configuration, things like that. What you'll find is that a lot of new businesses, especially in the eastern parts of the world, are predominantly IPv6. However, in Europe, and I'm assuming in America as well, the transition to IPv6 is extremely slow. I mean, in the networks that I've worked for, it's there, preparations are being made for it. However, it's not going to be moved over to IPv6 until it's necessary. I hope you've enjoyed the video, and hope